In this video, we're going to take a look at several examples of evaluating indefinite integrals using integration by parts. Some of these examples will be a straightforward application of the integration by parts formula, and others will involve having to do the process multiple times or in conjunction with other techniques. The integral by parts formula says that we can rewrite an integral of the form integral u dv as the expression u times v minus the integral of v du. Essentially, we can rewrite our given integral in terms of another integral, and the hope is that this integral on the right-hand side would actually be a little bit simpler to compute. Usually, we'll be able to use some elementary antiderivative in order to evaluate it. The first step in using integration by parts is to break up our integrand into a product of two terms, which we'll call u and dv, in such a way that when we create du and v from those expressions and use the integration by parts formula, we end up with an integral that we're able to compute. As we approach any example using integration by parts, we should keep the following general guidelines in mind in choosing u and dv. First, we always want to pick u so that it can be differentiated, and we want to pick dv so that it can be anti-differentiated. If one of these two things is not possible, then we're not going to be able to find du or v, and therefore not be able to use the right-hand side of our integration by parts formula. In addition to choosing u and dv so that these two things are possible, we would ideally like to choose u so that du is a simpler expression than u, and that v is a simpler expression than dv. This will give us the best chance for the integral of v du on the right-hand side to be a simpler integral than our original integral, the integral of u dv. Be aware that we might not always be able to follow these final two guidelines, as we'll see in our first example. In this example, we want to evaluate the integral of x natural log x dx. The first step in any integration by parts problem is to identify the part of the integrand that is represented by u and the part represented by dv. In this case, we have some choices. One choice would be to let u equal the expression x and dv the expression natural log x dx. This seems like the most natural first choice, but upon a little bit of reflection, we see that we're going to have a problem. If we pick dv to be the natural log of x dx, then in order to find v, we need to know the antiderivative of the natural log function, which is not something that we readily know. And so when this is the case, this tells us that dv cannot be the natural log function, and so we need to make a different choice. And so here, our only option is then to pick natural log of x to be u and x dx to be dv. This will allow us to both differentiate u and anti-differentiate dv in order to have all of the terms that we need to apply integration by parts. So if we go through the process here, we have u is the natural log of x, and dv will be x dx. We can differentiate u to get 1 over x dx. That's the derivative of the natural log function. And v is the antiderivative of x, which will be x squared over 2. Now, this does seem to violate that final guideline from the previous screen that said v should be simpler than dv. But notice that this is a case where we really don't have a choice because we need to pick u to be natural log x since we do not know an antiderivative of natural log x. Now once we have u dv picked, we form du and v. We can simply apply the integration by parts formula, which says that our integral is going to be u times v, which in this case is natural log of x times x squared over 2, minus the integral of v du, which is x squared over 2 times 1 over x dx. Right, we can now simplify this and evaluate this new integral. Our first term, we can reorder x squared over 2 times the natural log of x, just to make it a little bit cleaner. And we want to subtract from that the integral of x over 2 when we cancel the 1 over x with one of the x's from the x squared. This is now a relatively easy integral to compute. So we have x squared over 2 times natural log of x minus x squared over 4. And of course, since we're doing an indefinite integral, we do want a plus c added on, our arbitrary constant. And so the integral of x natural log x dx evaluates to x squared over 2 natural log x minus x squared over 4 plus c. If you'd like to try a similar example, you can pause the video and try to evaluate the integral of x e to the x dx. The full solution will appear in a few seconds. We can choose u to equal x and dv to equal e to the x dx, and then that means that du will equal dx and v will equal e to the x, since the antiderivative of e to the x is itself. Substituting all of those values into our integration by parts formula gives us the integral of x e to the x dx is equal to x e to the x minus the integral of e to the x dx, and that integral is just e to the x. So our integral evaluates to x e to the x minus e to the x plus c. In this example, we want to evaluate the integral of x squared e to the 3x dx. Our first step is to choose u and dv appropriately, and we can follow along kind of the same guidelines as in our previous example, where here we're going to pick u to be our polynomial part, x squared, and dv to be our exponential part, e to the 3x dx. Once we have u and dv set, we can find that du is the derivative of x squared, which is 2x dx, and v is going to be the antiderivative of e to the 3x, which will be 1/3 e to the 3x. Using these values, we can see that the integral of x squared e to the 3x dx will be equal to u times v, which will be 1/3 x squared e to the 3x, minus the integral of v du, which we have a constant of 2/3, which we can put outside of the integral. And then the integral will be of x e to the 3x dx. Now at this point in previous examples, we've been able to simply evaluate this new integral because we were able to find an antiderivative of the given integrand. But here, x e to the 3x is a bit too complicated to simply just find an antiderivative. It is worth noting that this new integral, the integral of x e to the 3x, is more simple than x squared e to the 3x. And so we have created a simpler integral here. We just don't have one that we're able to evaluate immediately. Since we have an integral of the same sort of form that is simpler, we think we're on the right track. And so what we're going to do here is apply integration by parts again, but now to this new integral, the integral of x e to the 3x. When we do that, we're now going to let u be x, dv will be e to the 3x dx, and so du will simply be dx, and v will be 1/3 e to the 3x, just like it was before. Now when we do that, we see that the integral of x e to the 3x by integration by parts will be u times v, which will be 1/3 x e to the 3x, minus the integral of v du, which will be 1/3 e to the 3x dx. This new integral is one that we can, in fact, now evaluate, since it's just a constant times an exponential. So this will equal 1/3 x e to the 3x minus 1/9 e to the 3x plus c. We get a 1/9 because when we integrate e to the 3x, the antiderivative gives us another factor of 1/3, which combines with the given coefficient to form 1/9. And now that we have this expression, we can simply take this expression for the integral of x e to the 3x dx, substitute it in to the first integration by parts formula, and obtain a formula for our given integral. So we start with our first integration by parts formula that says our given integral of x squared e to the 3x dx is equal to 1/3 x squared e to the 3x minus 2/3 integral x e to the 3x dx, and then substitute in the appropriate expression for this new integral. So we have 1/3 x squared e to the 3x minus 2/3 times the quantity, 1/3 x e to the 3x minus 1/9 e to the 3x, and then all of this plus c. And for purposes of problems like this, it's certainly reasonable to just leave your answer in this particular form. We've evaluated our integral, and we have a function here, even if it's not quite as simplified as it might be. But there's really no reason to do any kind of simplification once we have our final value for our integral. If you want to practice a similar example, you can pause the video and evaluate the integral of x squared sine x dx. The solution will appear in a few seconds. We start by letting u equal x squared and dv equaling sine x dx, which gives us du equals 2x dx and v equals negative cosine x. Substituting all of those into the integration by parts formula tells us that our given integral is equal to negative x squared cosine x plus the integral of 2x cosine x dx. Like in the previous example, we're not able to compute that integral directly, so we apply integration by parts a second time. Here we pick u to be 2x and dv to be cosine of x dx, so that du is 2 dx and v is equal to sine of x. Substituting those into our second integral, we see that we get 2x sine of x minus the integral of 2 sine x dx. And this integral is one that we can easily evaluate since we know an antiderivative of sine x is negative cosine. And so this gives us that the integral of 2x cosine x dx is equal to 2x sine x plus 2 cosine x. We then substitute this expression into our first integration by parts formula for our integral, and we obtain a final value of negative x squared cosine x plus 2x sine x plus 2 cosine x plus c.